We now see a slide of our presenter, Linda Griffiths. She's going to be sharing with us the session she would have shared in Dallas, but what a great opportunity for us to be able to share it here today. Throughout her session, I will be monitoring the chat. So if you have a question for Linda, a comment to share, I'll be able to read it and pass it on. So use your chat panel over at the right, and then you can we can pass that on to Linda if she doesn't have a chance to see it herself. So Linda, I'm going to give it to you here. I'll put up one more slide for those people joining us today engaged in social media. There are some opportunities for you to share what you're learning today.
Okay, I'm so excited to be here this afternoon. I know we're all disappointed that we didn't get to go to Dallas, but I think it's great that we're having this opportunity to share. I've been in education for over 40 years now and have just recently retired. I realize I'm going to probably become obsolete in another few years, but I thought this afternoon what I would share with you is some of the ways that I have attempted to increase student engagement in classrooms as a math consultant working pretty much in a coaching role with teachers. We all know that student engagement, if we can get students more engaged, they're going to learn more. And we've all seen all the cartoons and things about the disengagement of students, how they're sitting in class with their heads down and those kinds of things. But we really need to try to get our kids as engaged as we can. And the work I'm going to show you this afternoon primarily comes from two sources. I have to figure out how to get my screen to advance here. The first one is the principles from NCTM, the Effective Mathematics Teaching Practices. Establish mathematics goals to focus learning, to implement tasks that promote reasoning and problem solving, to use and connect mathematical representations, to facilitate meaningful mathematical discourse, to pose purposeful questions, to build procedural fluency with conceptual understanding, to support productive struggle in learning mathematics, and to elicit and use evidence of student thinking. I also rely heavily on the work of Peg Smith with her 5 practices for orchestrating productive mathematical discourse. And they are anticipating what students would do, monitoring as students work and problem solve, select different approaches that students have taken in the classroom to share, sequence them in a way that brings out the mathematics, and then make connections between the different representations. So to try to look at these and how they promote student engagement, we're going to look at a couple of example problems this afternoon. The first one is called compacted cables. And the setup for the problem goes something like this. Many cables can be compacted together to make bigger, stronger cables. The stronger cables are used in the construction of bridges and tall objects that need to be anchored to the ground. The diagram on the next slide is a size 4 hexagonal compacted cable made up of 37 strands. The questions we're going to try to answer in this problem are how many strands are needed for a size 12 compacted cable and how many strands are needed for a size N compacted cable. In other words, if you know the size of the compacted cable, how can you predict the number of strands of wire you're going to need to buy? Okay, so this is the picture that goes with it. Again, this is a size 4, and you can see where that comes from. Along the edges, there are 4 cables, and it's a hexagonal shape. It takes 37 strands of wire. So I know it's awkward to have silence, but we'll have about 10 seconds or maybe 20 seconds while I let you look at this and think about how you might approach this problem. Okay, so I did this problem in several Algebra 1 classrooms about 18 months ago, and I'm going to share some student work with you. So I want you to know this. In these Algebra 1 classrooms, we were studying modeling with quadratic equations. And so since this was in the unit on modeling with quadratic equations, and when I posed the problem, the class automatically assumed it needed to be a quadratic, but they weren't sure why or how to go about finding it. So to promote productive struggle, they kept asking me, is it quadratic, is it quadratic? And I kept saying, we've been studying quadratics, so it might be, but we've also studied some other things, some linears and different things. So you might want to think about those things. And as they began to work, now they were working in pairs, or I think there were one triad involved because of the number of students in the class. I find this particular problem, I engage students more if I pair them rather than if I put them in larger groups, because the conversation is what's happened, but each student needs to be thinking and interacting with one another. So I really prefer pairs, for this activity. So my first group began by looking at making a table that looks something like this. They looked at the size 4 cable, and I'll backtrack to that slide for a minute, and you can see there's 4 on the first row, 5 on the second one, 6 on the third one, then there's a row of 7, and then the 6 and the 5 and the 4 repeat. So they wrote their numerical representation for that model as the quantity 4 plus 5 plus 6 doubled plus 7, and they got the 37. Then they actually drew together and drew out the 5th one and saw that it was the middle row was 9, and that the 5, 6, 7, and 8 rows repeated. And they wrote a similar mathematical or numerical expression and got 61. Then they began to share the work. One of them did 6 while the other drew 7, and then they predicted together what the 8th one would be. And then they went into their TI. We had 84 calculators that day. So I'm going to show you some screens that I captured from their calculator. So now L3 and L4 were not in their calculator when they began. They had the 4, 5, 6, 7, and 8, and the 37, 61, 91, 127, and 169. And they proceeded to run linear regression, and they called me over. And you'll see that the result, that their linear equation was 33 times the cable size minus 101, and their R-square value was 0.988, which, if you're doing approximate modeling, is a very good model. They also, if you'll look at the bottom left-hand screen, they had the blue graph that was their linear model, and then they had the squares that represented their actual data. And they said, well, we think this linear model is pretty good, but it doesn't fit exactly. So I asked, do you think it should fit exactly? And one of the 2 students said, yes, ma'am, because there's going to be an exact number of wires in each one of these bundles. And then he said, you think we should run quadratic regression? And I said, well, what have we done that would help you know if quadratic might be a model? And they immediately remembered that the day before we had worked on first and second differences. So they created their L3 and L4 columns, and they were pretty confident at this point that because their second differences were a constant, they were pretty confident that that this was a quadratic. So they ran quadratic regression, and you'll see that they got 3x squared minus 3x plus 1, and their R squared it's a perfect fit. And I said, at this point, they said, does that mean we have it right? When I returned to their table after a few minutes. And I said, well, do you think do you have enough data to be sure? And they said, well, maybe not. But then they said, well, but we have the data that we have, and the red curve goes exactly through. All these match exactly. And I said, well, that's pretty good. And I said, well, can you answer the question now for me about 12? And so they got their calculator out, and they did, a little bit later, their screen looked like this. They had typed in, they knew they began with 12, and they knew they had to have 11 add-ins. And so that's all typed in. You can't see it on the screen, but they got 397, and they plugged 12 into their model and got 397. So they were pretty confident. At this point, they asked me, is there any way to get the calculator to add these numbers up in general, like for the variable n? And I went and got my TI Inspire calculator that I had one of, and we talked a little bit. They didn't know anything about summation notation, so it took about 3 or 4 minutes of discussion, but they eventually worked and did this. And they were very excited. They knew that in their parentheses, their first number was always the cable size X, and the last one was always 2 less than double the cable size, and that you had to double that, and then you had to add 1 less than the double of the cable size. And when they got this equation right here, they were really excited because they had gotten this more than one way. I did let this group present first when we began sharing out. And the reason I did is because the focus of my lesson was on knowing to suspect a quadratic model if your second differences were constant. So since that was my focus of my lesson, I really did have two focus points. One was to go back and revisit the first and second differences, but another goal was for them to get to understand another reason why something might be quadratic. So my second group that I visited with, when I walked up to them, they were sort of puzzled and getting frustrated with the numbers. And I asked them if they could decompose the hexagonal shape in any way that might help them count the number of wires. And so their work looked like this. For the size 4 cable, they saw 3 parallelograms, 2 of which were rhombi. One of them was a 4 by 4. Now the base is 4 and the height is 4, in the way they're looking at it. So their first parallelogram was 4 by 4, 4 sets of 4, which gave them 16. They had another one that was 3 by 3 and another one that was 4 by 3 in counting their little squares. And so they generalized that. They said, well, in size 4, you multiplied 4 times 4. So in size n, you would multiply n times n. Then you multiplied 1 less than 4 times 1 less than 4, and the 4 times 1 less than 4. So they also derived the same mathematical model, 3n squared minus 3n plus 1. I had noticed another group that was working very diligently, and they had a picture that looked like this. They saw that one in the middle is not fitting, but then they saw that you could divide it into 6 triangles. And I think because it was a hexagon, and maybe because of their experience in other classes, they were seeing it as 6 triangles slid together, which I know that's what they see in elementary school when they decompose these geometric objects. So they decided that each triangle was half of a, in this case, a 4 by 3 parallelogram, but they said in general it would be an n by n minus 1. And so they did since it was half, they divided that by 2, but there were 6 triangles, and then they had to add their 1 circle in the middle. So they shared this, and then immediately I had about 6 groups working, but I only was going to have 3 groups share out. The other groups had done something similar to the geometric approaches. So the group that had shared first immediately looked at me and said, we could see 2 trapezoids, but we didn't know how to find the area of a trapezoid. So we talked a little bit about that and thought a little bit more about it and did a little mini lesson on how to do that. And then up on the whiteboard, I didn't take a picture of it, so I tried to recreate it for you in this next slide. But up on the whiteboard, they said, okay, for the size 4, the top trapezoid was a base of 4, base 1 was 4, and base 2 was 7, and the height was 4. And so they calculated that and got 22. And the bottom trapezoid was 4, base 1 was 4, base 2 was 6, and the height was 3. And they got an area of 15, and the 22 and the 15 added up to their 37. So then they thought, okay, they said, I think we can do this for the general case. So they said, so what they were calling their top trapezoid would have a base of, their top base would be n, and their bottom base would be 1 less than n, and the height would be n, and they did the algebra and got 3n squared minus n over 2. Now their bottom one, the base would also be n, but it would go up 1 less, so the height would be n minus 1, and it would be 1 shorter, so it would be n minus 2. And they did the algebra and got 3n squared minus 5n plus 2. And then when they added those two expressions together, they got 6n squared minus 6n plus 2, and when they divided by 2, and then they got the same expression. So they were all really excited, and the class was pretty much engaged, and I'm not going to say pretty much, they were engaged, and they were successful with the problem in a variety of ways. Everybody in the classroom found out the answer for the 12, size 12, and the one group that didn't get to the generalization was very close when I had to call time because of the class timing mechanisms. But the main thing they got excited about is they began to think about the fact that we measure area in square units, and then quadratics had a squared term. And so they began to see that one time we would use an area model is when we could reduce a problem to an area model. So I was really excited about that. And the reason I wanted to share this with you this afternoon is because I think we can look at those effective strategies and relate them to this compacted cable problem. My goal was to model with quadratic equations. And the way I think this promotes reasoning is, why would this model be quadratic? I mean, a few days before, we had been working on creating quadratic models in different ways, but why would this particular one be quadratic? And I think it helped them to think through it a little bit more. Then the second thing, the different representations, is we started with a picture. We were able to create numeric, algebraic, graphical, and geometric models. And the students in the discourse piece, the students were trying to connect all their methods that produce the same models. There was lots of discussion about how are these alike and how are they different. Now, the one thing about trying to promote student engagement and choosing these activities is you have to anticipate what students are going to do. And then as you anticipate that, you have to, the really important piece of these effective strategies is that pose purposeful questions. And that is really, in my teacher training a very long time ago, I learned a whole lot about standing up in front of the group and performing, working problems and showing them how I worked the problem. What I needed to know and what I had to develop in my career was, how do I pose questions to students that allowed them to experience success without me having direct modeled how to do it before I gave them the problem. And this posing questions piece is really key. And so some of the questions that I had thought about ahead of time for this problem were these. Why do you think this might be quadratic, besides the fact that that's what we're studying? And then when they were working with drawing pictures and counting, I'm asking, can you predict what the size 12, the number of cables in size 12 would be without drawing the pictures? One of the questions that I ask often is, how's the last number in the sum related to the size of the cable? Because some of my groups struggled with seeing that last number, how it was related to the cable size. Then I had to ask, when they were dividing it into a top and a bottom and a center row, how can you predict the length of the center row from the size of the cable? And then with my groups that were trying to work from the picture, I had to ask them about how they would decompose the picture to help them in some way. So the main thing is, when you find a new problem or task that you think has the potential to increase student engagement in your classroom and to get at some of the important mathematical ideas that you're trying to get across to students, the first step is you must work through the task yourself. And you can't just, if you can only come up with one way to work the task, it's not a problem that's going to engage students, because it's one way, or it's my way or not at all. You need problems. If you really want to promote students engaged in the classroom, there has to be more than one way to approach this, so that our thinking is not all the same. And as you work through this problem and try to work a problem in many ways, it's really important that you think about, what did I think of? How did I get to decide to take this approach? What did I do? And then write a question around that. Now, I'm going to tell you, I worked many years as a pre-service teacher preparer, faculty member, and we spend a lot of time on lesson planning. And I get frustrated sometimes now that I was at the university for 28 years training teachers, but at the same time I was running an outreach center. And the last 2 years I spent in classrooms as a mathematics coach for a group of teachers, or rather, well, it's a long story, but I was coaching. And I began to understand that my lesson planning time could be spent more profitably if I worked on working through a problem, looking at different ways to do it, thinking about questions I might pose, thinking about what I think my students are going to do, then filling out some paperwork lesson plan. And now that I'm retired, I guess I can safely say that. I think sometimes we ask teachers to fill out paperwork when what we really need them to spend their time doing is thinking. I mean, what if I was an administrator, what I would want from my teachers is, what are the list of questions that you're prepared to ask your students to help them engage in this problem-solving process? So the purposeful questions piece was one of the hard things for me to begin to understand, how to pose those purposeful questions. Okay, I wanted them to build fluency by understanding they could use first and second differences to determine if something might be quadratic. That was my fluency piece, but I just didn't want to say that. I wanted them to come to understand that through some kind of conceptual understanding. And the main thing is to promote productive struggle, you walk a fine line. You've got to be able to come up with a problem that is challenging enough that it is a problem. It's not just another one like we did yesterday, but it's got to also have multiple entry points so that students can begin to work on the problem and struggle a little bit without becoming frustrated. There's a fine line between struggle and frustration. If I don't know where to start, I'm frustrated. But if I have a plan and begin to work, I may have to struggle to make that plan work. And the best ways I found to elicit evidence of student thinking is to ask students to work together, which forces them to talk aloud. And then as they are working together and talking in their pairs or triads, I need to be out of, I laugh and say, need to be out among my peeps. I need to be out there listening to what they're saying, and that's how I'm going to know what they're thinking. I need to be listening to their conversations. And I'm a big talker, and but it was hard for me to understand that my role as teacher might be to listen more and talk less. And then finally, I think it's important that you ask students to share their thinking with their colleagues, the other students in the class, so that they can see different approaches to the problem. Now, some of you, this is obviously, I was working in secondary classrooms, but you know about an approach that elementary teachers use called cognitively guided instruction, which means instruction is guided by student thinking. And that they also, in their training, do a lot of talking about having students share out. Well, I always know I'm in trouble when I'm in a classroom and I hear these words, who wants to share? It's not about who wants to share, guys. It's about who needs to share. Who has an approach that's going to help us get at mathematics? And every group doesn't have to share. If two groups take a very similar approach, then you don't have to have both of them share. You can just recognize the work of one group. Okay, and I think I've already talked a lot about this, but when I first began trying to orchestrate this productive mathematical discourse, I had to do something really weird. I had to work really hard at finding my problem and trying to anticipate what my students were going to do. Then I had to often pose my problem in the middle of the class and let them work on it so I could monitor them. And then when class dismissed, then I had time to do step 3. And that is thinking about the order in which you want the students to share their work. I've gotten better at it now that I can start a problem at the beginning of class and I can sequence my problems. I can select my students to present and sequence them on the fly. But that was a learned process. It didn't come naturally to me. And then the final thing is connecting those different approaches and making the mathematics clear. So I find that when we're trying to increase student engagement, the best way to do it is by problem posing and by encouraging students to talk to each other. And so I'd like to look at another example that's a little bit different.
Linda, this is Ruth. Pardon me for popping in. I'm just going to share a few comments that people have been sending into the panel. Excuse me. Michael from Missouri says that in his classes, we did work this year on thinking about questions to ask students to verify what they know and to advance their thinking. So that goes right along with your discussion of thinking about good questions and good problems.
Yeah.
Another participant, Peter from Texas, says, I love your comments about the importance of multiple strategies and purposeful questions in engaging all students.
Thank you, Peter. Okay. So I think we'll have time now, I think, to look at one more problem. And I encourage any of you that have questions or comments to, Ruth's kind enough to monitor that chat for me. Feels like I'm just sitting up here talking to myself, but I'm trying to remember all of you out there in the audience with me here. Okay, so the next problem I want to look at is this one. It's called the paper folding problem. A sheet of 11 by 8.5 paper is folded so that the upper right-hand corner is touching the bottom of the page. How far from the lower right-hand edge will the corner touch to produce the right triangle with the largest area? And I apologize that this is a picture that I had to take in a hotel room a few years ago because I was going to teach in another teacher's classroom the next day, and I wanted them to be able to see my approach, and this was the best piece of paper I had at the time. But anyway, so this is a problem I posed. Now, this was a Algebra 2 classroom. It was near the end of the year, and we were working with radical functions. And obviously, since this is a right triangle, the Pythagorean theorem might come into play, which might give you a square root, which might produce a radical function. But this was a very diverse Algebra 2 classroom. And I have decided that in these small rural schools where I work, there's often only one section of the class. And anyway, I appreciate the diversity, and I find that and when I'm talking about diversity here, I'm talking about in their background, in their previous success in mathematics. Not everyone in this classroom had been terribly successful in their previous work with mathematics. They struggle. Some of them really struggled hard. And so in this classroom, I was always looking for a problem where there was a very concrete approach. And so one of my groups that often struggled asked me, is there any way we can guess and check? Because they had discovered that they could often get a right answer without doing the algebra if they could, and a lot of times because they were guessing and checking, their arithmetic work would lead them to the algebra. So I said to them, well, why don't you just think about where you want to fold it and then fold it, because they had several sheets of paper and they had a ruler. And I said, and then measure the height and calculate the area and then see what you can do. So they worked really hard. And I have to tell you that many of you, if you've had classroom experience, know that anytime a ruler comes out, even in a high school Algebra 2 classroom, reading that ruler is a constant challenge. So we had some, I remember this day very well because they needed to measure pretty accurately and they were really struggling to do that. But this is the table that they came up with. They thought, since the paper was 8.5 by 11, they thought that the largest area triangle would happen if they folded it to the middle, which made the base 5.5. And then they proceeded to measure the height. Well, I have to tell you that I happened to be standing there when they measured it, and the first measurement they got was 2.5. And there was this big argument about, well, it really wasn't quite 2.5. And one of them said, well, it must be 2 3/8. And another one said, well, it's more than that. It's closer to 2.5. And one of them says, is there anything between, is there any other thing between that? And one of them said, my dad says this is marked off in 16ths. Well, and, so they argued about it, and they came up with, if they went to 16ths, that 7/16 was just a little bit less than a half. And then they used their calculator to find out that that would be 43 75 10,000ths, and that's where they got that number. And they calculated the area with their calculator. And then they measured 5, and they were pretty sure it was 2 3/4, and they were really surprised that they got a larger area. So they thought maybe 4. So they tried 4, and it got smaller. Well, then they tried 4.5, and it still wasn't as big as their 5. And by the time they had done all their folding and measuring and punching in their calculator, they were getting frustrated, and they said, we think that 5 will be good. So they decided that the base would be 5 and the height would be 2 3/4, and that the area would be 6 and 875,000 square units. So they were a very hardworking group, and I let them share first, and I want to tell you, I'll show you why in a minute. So my other groups all took a very similar approach. They tried to do it algebraically, and they all struggled with the same thing. If we go back to this slide, since they were looking for the length of the base, they wanted to let that be x. And when they let that length of the base be x, they couldn't calculate the area without introducing another variable because they didn't know, they couldn't figure out because they had two other unknowns. They did know the two other unknowns added up to 8.5. And so finally, one student in one of the pairs that was working said, I think we should let the height be x. And he said, and when we finish, we have to remember that we're going to have to go back and calculate this base length because that's the answer to the question. And then they were immediately successful because they didn't have to introduce a second variable because they had the height at x and they had the hypotenuse at 8.5 minus x. Then they could use the Pythagorean theorem to get an expression that represented the base. I thought that was, and then since all the groups were struggling, I started sending representatives from other groups to the group that had come up with making the height x to ask them what they were doing to overcome the problem of needing really three variables because they wanted to vary the area. And they, of course, were not able mathematically to handle that. I had purposefully done this because I wanted them to have a discussion about defining variables. But anyway, my other group, this is some of their screens that I captured. They wrote this expression you'll see in the screenshot on the left. They too were using 84s. Most of my schools in Arkansas still have 84s in their regular. They've gone to the Inspires in their calculus and pre-calculus, but they're still trying to use those 84s that they had. So they came up with this expression where the expression they came up for using the Pythagorean theorem for the base was the square root of the quantity 8.5 minus x squared minus x squared. And then they multiplied that times the height, which was x, and divided by 2. And the interesting struggle, the productive struggle, was in setting the window. And to see this, they finally came up when they, just let the window be what it was, whatever it happened to be on the calculator. They weren't seeing good pictures. And they finally decided that the height had to be between 0 and 4 1/4. They wanted to go a little on either side of that because if you fold the 8.5 side down flat, it falls down, it's 4 1/4. Anyway, so they set that, and then they had to struggle a little bit with trial and error to figure out this particular group selected an X max of 9. So you'll see on the bottom left there, their graph where they've used the maximum command. And they found that if the height was 2.833348, then they'd get an area of about 6 95/100 square units. And then the problem they had then was I didn't ask them what that height was. I'd ask them what the base was. So up in the upper right-hand corner, hopefully you can see they wrote an expression that represented the length of the base, which was the square root of the quantity 8.5 minus x squared minus x squared. They graphed that, and then once they had the maximum, they used the down arrow key to find out that their height would be 4.907477. Now, it's really interesting to me that the thing they struggled with was after I found that height that produced the maximum area, how was I going to find the base? And so it was really interesting. I think we learned that wasn't my original instructional goal in this problem, but I really believe that my kids in this problem learned more about defining a variable than they did maybe even about what I hope they would learn. But we were studying radical equations. We were studying radical equations, and we did use the Pythagorean theorem to produce a function that included a radical. We looked at the shape of that graph and found that this particular one did have a maximum. We were able to find it. Thought we did a lot of really good mathematics. So in thinking about the effective strategies and how it related to this problem, not the compacted cable problem, I now see a mistake in my PowerPoint. That should say the triangle problem. The goal was to model with a radical function and maximizing a function. And then I wanted them to talk a little bit about why this model would be a radical function. We were able to use a variety of representations. The one group was they worked strictly with concrete and pictorial and numeric representations, but we also got algebraic, graphical, and geometric. Now, an interesting thing happened with this problem. I was also working with another teacher that same day in the same building with a geometry class, and the group that was measuring and getting the estimates, they said, is there any way, they said, it would be neat if we could just take this piece and move it along the bottom edge and automatically do the calculation. And I said, well, I think we can do that with some dynamic geometry software, with the TI dynamic geometry software, but we won't have time to do that today, so you're going to be limited in what you can do. But I went to the geometry class, and this was a pre-AP class, and so they really like challenges. So I posed this problem to them and challenged them to create a T3IC file that animated moving that point along and calculated the area. And they were very successful in doing that. And if we had been in person today, I was going to pull up my file and show it to you, but I'm just going to let that go for now. But this is a problem that could be posed in different ways to different classes. I guess I just want you to know. So, and actually an animated version of this is very possible. The discourse, students were discussing how to define their own known and why can the final answer not be their X, and the need for more variables. And that was a really good mathematical discussion in that classroom. Again, purposeful questions. As I worked through the problem, thought about it, I wrote down some questions. You can see on the screen up here some of the ones that I thought about. Again, it's very important that we as teachers take the time to have in our mind some questions that would be purposeful that we could ask, because we're not always going to be able to come up with those on the fly, I'm afraid. Okay, I wanted them to be able to fluently apply the Pythagorean theorem, but I wanted them to do it from an understanding perspective, or help them understand something. Again, the same things on these slides. Don't tell them how to do the problem, but by the same time, ask them to work together, listen as they talk. Another key thing that has helped me with eliciting evidence of student thinking is in the classrooms where I have had access to the TI Navigator, the ability to pull up the classes' screenshots and see where they are on their calculator screens has been invaluable to me in helping me find groups that were taking similar approaches that might want to collaborate with each other. If you haven't used the Navigator, it's a wonderful, wonderful tool. Now, I know I've talked a lot about how much work this all is, but I have a couple of other thoughts that I'd like to throw out there and maybe get some of your reactions to this. We spend a lot of time on curriculum development, but if we choose good problems that fit mathematically into our curriculum, that do promote the mathematics that we're trying to teach, and we work with groups and we have evidence like I have today of approaches that students took, and we preserve those, then each year gets easier because we won't have to do so much anticipating because we'll have the work that we did from last year. We'll be able, I really am beginning to think that curriculum development could take a whole new turn where not only do the instructional materials include examples of problems, but they include examples of different approaches that students in the past have taken to the problem. The other thing that I didn't see so much in the PowerPoint that I created for today but I'd like to point out to you is I think sometimes we forget the fact that uh, sometimes the wrong approach or the wrong answer tells us more mathematically than the right answer did. With the maximizing the area of the triangle problem, students that were trying to let the base be their unknown got very frustrated. They not only struggled, they were getting frustrated, and because they couldn't represent the other two values they needed to know with that one variable. And I think that that discussion, that fact that I can't make this work, was actually a more valuable discussion than when we did make the little tweak and we did make it work. Now, I've used this problem about 7 or 8 times in classrooms, and out of one time, I had one student that was very successful in letting the hypotenuse be the unknown and then defining the base and the height in terms of that. So that's another approach that no one in the class that I'm telling you about today did. But I have a lot of hope for the future as groups work together and try to. I think we have to think about how do we really get students to be engaged in learning. And I've told this story before, so some of you that have been to my sessions, I was in a school in Arkansas, and that day I was the guest of the superintendent, and my goal was to visit some classrooms, and he and I were going to have some discussion about what kind of professional development we thought might be beneficial. So I visited an Algebra 2 classroom where they were trying to learn to factor quadratics with a leading coefficient of 1. And so there were a lot of adults in the room that day. I was in there, the superintendent was with me, the principal was with me, and a curriculum coordinator. And we were in the room, and we had stationed ourselves in various places to be as out of way as we could. And I was sitting very near a young man, and the teacher had posed a problem and asked them to factor it. She had 2 pieces of those big paper up on the wall with 16 steps for factoring a quadratic. And this young man was sitting there, and after she put them to work on the problem, they were working alone, and he had his pencil, and he was kind of moving it, but he wasn't touching the paper. And so I leaned over and said, "What are you doing?" And he said, "I'm waiting." And I said, "Well, what are you waiting for?" And he said, "Do you see that boy up in the front that's still got his coat on?" And I said, "Yes." "He's working the problem. In a minute, he'll raise his hand, and the teacher will ask him, and then I'm going to write everything he writes down to work the problem because I'm a good student." This young man saw being a good student as in waiting for someone that could do the work to do it so he could copy it on his paper. I asked him, I said, "Well, is there anything you know about factoring quadratics?" And he said, "I know there's going to be 2 sets of parentheses." So I said, "It wouldn't waste any lead in your pencil if you went ahead and drew the 2 sets of parentheses." He said, "No, ma'am." So he did. And I said, "Do you know anything else?" And he says, "Well, in every problem we've done the last 2 or 3 days, it's been an X in the front of each set of parentheses." And I said, "Well, is it going to waste you and your time to write that?" And he said, "No, ma'am." And I said, "Well, do you know anything else?" And he said, yeah. He said, "You're going to have 2 numbers in the back, and they're going to multiply to be," I think the number was 8. No, maybe the number was 6. I don't know. But anyway, he said, "They're going to multiply to be that number." And I said, "Well," he said, "Yeah, but," he said, "I'm not sure. It could be 1 and 8, or it could be 2 and 4. And I said, "Well," I said, "I'll get you some more paper and another pencil if you need it, but go ahead and pick a couple." So he picked, I don't remember exactly what he picked, and he said, "Now the real trouble starts." He said, "I don't know whether you put a plus and a minus, or a minus and a minus, or a minus and a plus." And he said, "If it's a minus and a plus, I don't know which one goes where." And I said, "Well, stick them somewhere." And then he had his 84 calculator laying there on his desk, and I said, "Put in the equations she gave you in Y1, put the one you've got now in Y2, and let's graph them and see if they're the same." Well, they were different. And he looked at him and he said, "Yeah, but I think I can fix it." And I said, "How are you going to fix it?" And he said, "I think I've got the minus where the plus needs to be and the plus where the minus needs to be." I said, "Well, try it and change it." And they matched exactly. So I said, "Raise your hand." And I said, "I'll protect you." He raised his hand, and she said, yes. And I said, he's got it. Let him show us how he did it. And he took his calculator up, and this was in the old days. He had to plug his calculator into the projector screen up at the front. And he told the class what happened and what he did, and he got the answer. And a little girl that was obviously a bit of a mess said, you can't do another one. And he looked back at me and he said, give me one. So I made him up one, and it took him 3. He had to adjust 3 times. He got it. And the little girl jumps up and she says, I want to try one. And she takes his calculator and says, you give me one. So I gave her one. And it took her a couple of times, and she got it. And now everybody in the class is going, give us one, we'll work on it. And there's 2 mad people in the room, and I'm going to tell you they are. They were the teacher and the boy in front with the coat on. But we were factoring, and they were experiencing some success. And they were engaged in the learning. They were talking to each other. They were sharing what they thought was wrong with the graph when they saw it. That's not the only example I can give you of times in classrooms where having access to this technology has been such a wonderful thing to get students engaged. And the end of the story is when the bell was over, the little girl said to me, I'll see you tomorrow. And I said, well, I won't be here tomorrow. And she said, well, that's a shame because I learned more today than I have all year. I don't think these kids don't want to learn. I think they want to learn. I think they're just not very good at mimicking behavior. They're better at thinking and problem solving and working together. And I think they want to learn. I think they can learn. I think our education system has a wonderful opportunity to do some changes in how we approach teaching and learning and make them even more effective. And this comes from a student who herself was very good at mimicking behavior. I'll be honest with you, I just thought math was a game. You learned the rules, you followed the rules, you looked for an example, you plugged into the example, and I was very successful at doing it that way. But I didn't originally choose math as my calling because I thought it was just, I didn't understand how it all worked. But when I did get a math minor, because you needed a minor back in those days, and couldn't get a job teaching history, so I ended up in math and began to understand the math, began to have productive struggles myself as a young teacher, and begin to understand that I never understood the math till I struggled with it. And I think that all the research we have, the new books that are coming out from NCTM and from many other researchers and authors are telling us that students can learn mathematics and do it meaningfully. But it may not all be about monkey see, monkey do. Okay. So I don't know what else we want to talk about today. The technology, I want to say that again about how, I mean, even the students that were doing the measurements on the triangles could not have calculated the area without a machine. Okay, Ruth, anything in the chat?
So, Linda, as we're getting near the final few minutes, we have opened up the chat, so we're inviting people to share comments, ask questions through the chat. Be sure when you select in the chat menu that you choose all participants. That way it'll go out and everybody can see it. Thanks so much.
All right, and then thank you all so much for coming, and I have really enjoyed doing this, and thank you, T.I., for the opportunity for us to get some sharing together. Thank you so much.
Okay, got some good things going on in the chat. Linda and I'll be looking at those, and you all can read them as well. When questions come up, Linda is still available to answer those. So, Linda, somebody was wondering, are your resources going to be shared on the TI website, where the education.ti.com, where the conference session files are going to be located?
I did upload those about noon today.
Great.
Yeah, the PowerPoint is there.
Great. Thank you so much. and I'll put a link for that in case somebody hasn't found it. Chances are, if you registered for these events today, you've already found those, the location where those are going to be posted.
Yes, and if they have any questions, if they get the PowerPoint and if they want some I also got just like handouts of the 2 problems that if they'll email me, I'll email those to them also.
All right. And if you want to enter your contact info in the chat there again, that'll work out. People will have it that way. Or if you just want to dictate it to me, I'll type it. I moved your slide around, so I don't have it anymore.
Okay, it's lindag@uca.edu. Even when you retire, you get to keep your university email.
All right, I'm going to put it in. If that's not correct, you just tell me and I'll fix it.
Okay, thank you.
We're seeing in the chat window now the link where you can get a certificate attendance for Linda's session today. You will also be receiving this information in email later. Information about how to access the recording of this session and information about your certificate of attendance. And I'll go ahead and put that link in the chat as well. Okay, we're still watching, seeing if there's some other questions and comments coming through. Thank you all. Good comments. Okay, Linda's scrolling up and down here. I'm reading comments. We're able to share them and maybe.
Okay.
All right.
Okay.
So one of the participants is wondering, what are your thoughts on a follow-up after going through one of these lessons? Maybe that's addressed in some of your handouts or subsequent slides that you might have provided.
Well, I mean, what is so hard for me right now is when I was trained, I was taught to think about a lesson in terms of one class period. But I'm beginning to think now more in bigger chunks, like if I want students to understand quadratic modeling, how many examples do we have to look at? And then what does and neither one of these was that kind of lesson, but sometimes I think about, so we've been modeling with quadratics, what does that summary lesson look like? So for example, in the quadratic unit that I've worked with the school to develop, the summary lesson looked at the different situations in which we had used quadratic models, ones that could be related to area, like the one y'all saw today, ones that could be related in change, like minutes per second or per second, those kinds of more physics kind of examples, the different kinds of things that we came up with. And so really in following up with those students on those lessons, I think, and here's another thing that happened in some research that I did a couple years ago that goes to this. We had done a whole unit, this was a 6th grade unit, but we had done a whole unit on fractions, and we had set aside a certain amount of time in the classroom. Well, the first 5 lessons were just interminable. They were taking multiple days to do, and the teacher was getting nervous about getting finished, and we were getting nervous. And finally, about day 6, after we got to about the 6th lesson, we started being able to do 2 and 3 of the tasks a day, because the students, because of that time we spent on the front end, really focusing in on understanding, when we got toward the end of the lesson, because so many of the students had that deep understanding, the tasks were going so much faster that we did end up being able to complete that unit of study in the amount of time that had been set aside in the pacing guide. So slow at the beginning, you know, it's slow and steady at the beginning will win the race in the end.
All right. Thank you for sharing that, and thank you all for sharing comments in the chat over there. We look forward to seeing you at future events, and we really appreciate your time here today at this session. And thank you, Linda.
Thank you, Ruth. I enjoyed it. Thanks very much.